So, welcome to today's physics seminar. The physics seminar series is sponsored by Eddie and April Lucas. And so we have the ability to bring in speakers to talk to us about various physics topics. The couple of talks we have early this spring, though, are interviewees for the condensed matter position. And today we have Myoung-Woo Yoo. He is here. So he grew up in Seoul, South Korea, and got his PhD at Seoul National University, working on reversal dynamics of magnetic vortex cores and soft magnetic nanoelements in 2015. He stayed in Seoul to the end of that year before starting a 5-year postdoctoral position at the Center for Nanoscience and Nanotechnology at Saclay University in Paris, France. There he used those magnetic vortices to develop nano oscillators. He also did measurements of the anomalous Hall effect and ferromagnetic resonances in ferromagnet superconductor hybrid systems, and made analytical and numerical calculations of fermions and vortex dynamics. Then in 2021, he became a postdoctoral researcher at the Material Research Laboratory of the University of Illinois, Urbana-Champaign, where he is working on estimation of thermal contribution to current-driven magnetization switching in antiferromagnets and the development of spintronic devices using antiferromagnets and chiral materials through transport of optical measurements. And he also worked on developing a micromagnetic model for antiferromagnets. Today, he will tell us about how spins move and carry information from magnetic materials to quantum and topological magnets. Please help me welcome Myoung-Woo.
Thanks so much. Yeah, thank you for a very kind introduction. Okay, good afternoon, everyone. My name is Myoung-Woo Yoo. I'm a postdoctoral researcher from the University of Illinois, Urbana-Champaign. Before I start my presentation, I would like to thank you for this opportunity to present my research program at the Wichita State University. Today, I will discuss how electron spins move and carry information in magnetic materials, and how this simple idea can be a foundation for spintronics technology. So my goal of this talk is provide you an intuitive picture, physical pictures of what spins do in solid materials and how their motions can lead to useful signals, and why magnetic materials can be the foundations for spintronics technology. So please feel free to interrupt me at any time if you have any questions in this presentation. So my research, today's my talk is organized into 3 parts. In the first part, I will discuss how spins move and carry information, mostly focused on ferromagnets as a starting point. And in the second part, I will introduce a different type of magnetic materials. The name is quantum magnetic materials. In the last part, I will briefly introduce my research program. It is symmetry-governed spintronics. So let me start with a very basic question. Why spin? So modern electronics is based. When electrons move, we obtain an electric current, and this electric current is the basis of the most of modern electronic devices, including your phones, laptops, computers, and any electronic devices. However, the electrons have another fundamental property called spin angular momentum. So you can think the spins as a very tiny magnetic moment or bar magnet associated with each electrons. So the spintronics is the idea of using the spin angular momentum, in addition to electron charge, to store and process information. So the word spintronics may sound like very futuristic, not real, but spin is already deeply embedded in our today's technology. So for example, the data centers of any internet services, the Google, social media, or cloud services, the data centers store enormous of information using magnetic memory. And such hard disk drives and magnetic random access memory, they store bit information, 0 and 1 bit information, by controlling the orientation of spins in magnetic materials. So a large fraction of world's digital information is already stored using spin. So spin is not just a scientific physical curiosity. It is already very essential for today's technology. Despite the success of charge-based electronics, there are fundamental challenges. Moving electrons in resistive materials inevitably generate heat. This is a heat dissipation or energy dissipation. As the device is smaller and faster, the energy dissipation becomes a serious bottleneck. However, spins can provide additional degree of freedom to electrons. So we can store information in the orientation of spin or the spin motion without the motion of electrons. So we can avoid heat dissipation, energy dissipation. So using spin may enable more energy efficient and new functional information process because the spin property is quite different with charge. One is scalar, the other one is vector. They are totally different. If we want to use spin for information technology, we need to understand how spins behave in solid. All materials like this consist of atoms, and all atoms have electrons. And each electron have a spin. In solid, spins are interacting with each other through quantum mechanical exchange interaction. And when spins show ordered pattern, we call the materials magnetic. If neighboring spins align in the same direction, we obtain ferromagnet. If neighboring spins align in the opposite directions, we obtain an antiferromagnet. So magnetism arises from spin orders, electron spin order. One of the most important message of today's my talk is that spins are not static. Even in a perfectly ordered magnetic materials, spins can change their direction, orientation with time. They can respond to external magnetic field. They can respond to electric currents. The time-dependent spin behavior is so-called spin dynamics. So one of the most representative spin dynamics is precession. So when a magnetic field is applied to spin, the spin rotates around the direction of magnetic field. Actually, this motion is very similar to how spinning top rotates around the direction of gravity, because both spin and spinning top have angular moment. So that's the beauty of physics. We can explain two totally different phenomena with one physical theory. However, in real magnetic materials, spins do not exist alone. Billions of spins are coupled together. So generally, the spins behave and moves together in a correlated way of, yes. Yes, I'm sorry. I hope you can see this collective motion. So we call this as the collective motion of spins in magnetic materials. Oh, thank you. Okay, it's much better. Thank you. So one of the most important collective motion of spins are spin waves. In spin waves, one spin rotates, then this rotation propagates through the material like a wave. So we can think the spin waves as a ripple traveling over the sea of spins. A key feature of these spin waves is that we can embed information in spin waves, and this spin wave can transfer information without the motion of electrons. No heat dissipation. So the spin waves can provide the possibility of low power information processing, and that's why the spin waves have attracted much attention in spintronics field. Spin waves are not just a passive excitation. We can make magnetic structure which can guide, route, and modify the spin waves. In my earlier work, I designed the spin wave routing device where one input signal is separated into two different outputs depending on their frequency. And this result clearly shows that the spin waves can be engineered and controlled, and this is very important for building information devices. Okay, so far we discussed about the wave-like behavior of collective spin excitations. There are another important or different type of collective excitations that it behaves more like particles. So the examples include magnetic vortices and magnetic skyrmions. the magnetic vortices and skyrmions are very stable and nano-sized spin texture formed by many spins, as you can see. It's formed by many spins. Even though they consist of many spins, the entire spin texture moves as a single object. So therefore, we called them as the topological magnetic solitons, means it looks like particle. So the magnetic vortices and skyrmions show particle-like behaviors, and they can have their own dynamics. They can oscillate, they can move under external magnetic fields or electric currents. We can talk about their position, velocity, and trajectory. More interestingly, they behave like a massive particle. So we can talk about their mass, and they show the inertial dynamics, and also their inertial mass, the mass can increase with their motion velocity. They show particle-like behavior. And the topological solitons particle-like behavior can be used for information devices. One example I worked on is nanocontact vortex oscillator. So the nanocontact vortex oscillator consists of one magnetic layer, thin film, with a nanocontact as non-magnetic. So once we apply electric current through the nanocontact to magnetic layer, I hope you can see the magnetic vortex in this magnetic layer, but there is. This electric current can excite the vortex oscillation motion. And of course, we can measure the oscillation motion by electrical method in the frequency domain and in the time domain. In this work, we found that we can control the vortex dynamics by controlling electric current amplitude, and also found that we can convert the electric signal into bit sequences. And these results show that we can use the topological solitons particle-like behavior for information applications. This is the random number generator. Okay, let me summarize the first part. In this part, we discussed how spins move and carry information in ferromagnets. So I show you that spins are not static. They can move, such as spin precession. And I introduced two representative collective spin excitations, wave and topological magnetic solitons behaves like particles. And I also show that the collective spin dynamics can be used for information processing. Okay, then let's move to the part 2. In the next part, I will introduce you a different type of magnetic materials. The name is quantum magnetic materials. So the initial question is, where is spintronics going? Of course, there are many active research field and very exciting research fields in spintronics. But one of the major field is the quantum magnetic materials. So quantum materials means the materials where classical physics is not sufficient to explain and understand their properties. So in this part, I will introduce quantum magnetic materials and how they can open new possibilities for spintronics. So in the previous part, I mentioned that spin orders can create magnetism, the ferromagnet or antiferromagnet. But the spin order does not create only magnetism. It also modifies spin symmetries of materials, like this. So once the symmetry is fixed, it determines which electronic band and spin splittings are allowed. And as a result, the spin-dependent band structure can lead to spin-dependent phenomena because of the quantum effect. And we cannot explain this using classical physics. So in this part, I will talk about quantum magnetic materials, which properties is governed by mainly spin symmetry. So in this work, I investigated antiferromagnetic materials. In antiferromagnetic materials, the neighboring spins align in the opposite directions. So generally, the antiferromagnets have zero net magnetization, nearly zero net magnetization, because they are all compensated. The zero net magnetization sounds like a very problem in spintronics because most of the spintronic phenomena rely on the magnetization. However, the important thing is that spins still exist in this material. Even though they have zero net magnetization, the microscopic spins are still present and ordered and dynamic. So the absence of magnetization does not mean the absence of the spin physics. Compared to the ferromagnets, the antiferromagnets have some advantages, also have some advantages. First, the antiferromagnets can show ultra-fast dynamics up to terahertz due to their strong exchange field. And also, they generate no stray magnetic fields, which can reduce the magnetic crosstalk to each other. So it is very attractive for dense integration. And also, they can be very robust against external perturbation. So the antiferromagnets can offer high-speed, low-noise platform. It sounds like very good. Do you know this guy? Yeah, his name is Louis Néel. He got Nobel Prize 1970 due to his work on antiferromagnets. In his Nobel Prize speech, he said, antiferromagnetic materials, interesting, but not very useful. Because generally, the antiferromagnets almost do not interact with external stimuli, magnetic field or electric current, because most of the phenomena locally compensated between the two different sublattices. So it has been very challenging to read and write spin information using antiferromagnets. However, recently, a different type of antiferromagnets have been reported, that is non-collinear antiferromagnets. The non-collinear antiferromagnets are special classes of antiferromagnets with, as you can see, very complicated, have very complicated spin texture. But they have nearly zero net magnetization because most of the components are compensated. despite the zero net magnetization, the non-collinear antiferromagnets can have spin-dependent band structure. In this case, density of state, but clearly we can see different density of state for upspin and downspin. And this means that we can read out the spin information using electric current because it responds differently for spin up and spin down electric current. Okay, now we can read out the spin state of this non-collinear antiferromagnets. But what is the spin state of this complicated spin texture? How can we define its spin state? At this point, we need to change our language. In the case of ferromagnets, the magnetism can be described by magnetic dipole because they have two poles, North Pole, South Pole. However, for the more complicated magnetic materials, we need to use higher order magnetic multipoles, such as magnetic quadrupole or magnetic octupole, septupole, kind of things. So the magnetic multipole order is determined by symmetry. But the important thing is the magnetic multipole is not just the mathematical construct. It actually determines the electronic band structure and the electronic property of magnets. Okay, now we can define the spin state of complicated non-collinear antiferromagnets. The next question is, how can we control the spin order? So recently, people found that we can control the magnetic multiple order, in this case, octupole order by applying electric current. So in this work, we studied the mechanism of the current-driven octupole switching in non-collinear antiferromagnets. And more interestingly, we clearly observe two different electrical responses here and there, and also clearly different optical responses here and there from different octupole states, such as octupole upstate and downstate. This result means that we can write information in non-collinear antiferromagnets using current. And we can read out the information using currents or light. So actually, this result is very important for the information applications. So in the first part, I introduced the topological magnetic solitons. The non-collinear antiferromagnets also can have topological magnetic solitons, such as magnetic domain walls or skyrmions. But in this case, of course, they are built by magnetic multipoles, not dipoles. So their properties are totally different with those in ferromagnets, but they still show particle-like behavior. We can use them for information applications. So to investigate the dynamical property of topological magnetic solitons in antiferromagnets, we developed the micromagnetic model for non-collinear antiferromagnets based on magnetic octupoles, not dipoles. So based on this model, we can conduct the numerical calculations of the domainal motion, and we can clearly see the domainal formation and the motion, particle-like motion. We know the position, direction, velocity, kind of things. Also, this micromagnetic model is much efficient than conventional atomistic spin model. So for example, in the case of the previous simulations, it takes about a few minutes for the simulation, but it'll take more than tens of hours if we use atomistic spin model. So this micromagnetic model can provide a foundation for predicting and analyzing multiple soliton dynamics before and after the experiments. The last question is, how can we see the topological magnetic solitons in antiferromagnets, the visualization? In the case of ferromagnet, conventional magnets, the magneto-optical Kerr effect microscopy is very powerful technique. However, in antiferromagnets, the Kerr signal is very small. So we cannot obtain sufficient contrast to see the topological solitons. So in this work, I and my mentee, undergraduate mentee, we demonstrated that the optical interference engineering using dielectric layer, in this case MGO, can significantly increase the Kerr signal like this. So careful controlling the optical stacks can achieve a very high enhancement factor, more than 4 of the Kerr signals. And these results can open the practical route for the topological soliton visualization in antiferromagnets like that. Okay, I will summarize the second part. In this part, I introduce you the new different type of magnetic materials, the quantum magnetic materials. The non-collinear antiferromagnet is the example, as an example. So I show that symmetry is very important in this type of quantum magnetic materials. And also I introduced magnetic multiple moments as a new language to describe this kind of complicated magnetic systems. So with this in mind, I will move to the last part, the symmetry governed spintronics. In this part, I will introduce my research program, symmetry governed spintronics. So in the previous slides, I showed that Louis-Nel mentioned that antiferromagnetic materials interesting but lacking functionality. But this perspective has been changing, and today people believe that antiferromagnetic materials can have symmetry-driven functionality. So my research program is built on very simple idea. Symmetry governs spin dynamics, spin transport, and spintronics. Spin symmetry leads to magnetic multiples and multiple dynamics. Structural symmetry can lead to spin angular momentum transport, and together they can provide selective multiple excitations for spintronic applications. So in my program, the first step is to understand the collective multiple spin excitations in quantum magnetic materials, such as non-collinear antiferromagnets. Instead of using conventional magnetic dipoles, I will describe the system and dynamics in terms of magnetic multiples. In this work, I will investigate the collective multiple dynamics in non-collinear antiferromagnets which can be interpreted and predicted by using micromagnetic model approach I have introduced in the previous slides. So that is our tool. The second step is to transport spin angular momentum in antiferromagnets using structural symmetry. In this case, I want to use chiral materials. In chiral material means actually chiral, the materials which have the chiral molecular or atomic structure. And in these chiral materials, the spin angular momentum of the electric current can be polarized parallel or antiparallel to the current direction. And actually, this spin information is determined by the structure, right-handedness or left-handedness. And this generated spin current and spin torque can exert as a spin torque on the adjacent antiferromagnetic layer. Thereby, finally, we can excite the magnetic multiple spin dynamics in antiferromagnetic materials. So from this, we can obtain the symmetry governed handle to drive the multiple excitations in antiferromagnets. The last step is selectively excitation and control the multiple excitations in quantum magnetic materials. In this case, we will use the spin torque, spin current and spin torque obtained from the symmetry governed technique in the previous step. And in this case, we include both spin wave-like dynamics and topological soliton dynamics. And our goal is achieve selective mode excitation and characterize them using electrical and optical waves. And I hope the results can establish a pathway toward the using multiple spin excitations for spintronic devices. My long-term goal is explore the collective multiple excitations using quantum sensing. In antiferromagnets, the multiple excitations can generate very small AC magnetic field, even though they have zero net magnetization. And this small AC magnetic field can be detected by very sensitive solid-state qubits, such as MV center spins. So my initial goal is identify and detect the multiple spin excitation in non-collinear antiferromagnets, including both spin waves and topological soliton dynamics. And I hope the results can be a potential bridge between magnetism and quantum systems. So my research program starts from understanding the spin dynamics in the antiferromagnetic materials and develop spin symmetry-driven spin transport and spin torque, and uses those two tools to achieve a selective excitation of multiple dynamics in quantum magnetic materials for spintronic applications, with a long-term goal towards coupling the multiple excitations to quantum systems. So I will summarize my last part. In this part, I introduced my research program, Symmetry Governed Spintronics, which consists of understanding multiple spin dynamics, developing symmetry-driven spin transport, and achieving selective multiple mode excitations using symmetry-driven spin torque with a long-term goal toward coupling multiple excitation to quantum systems. Okay, this is the end of my presentation today. And this is my current and former colleagues included in this presentation. Actually, they are my colleagues, my friends in UIUC. And he is my boss, Professor Axel Hoffman. And she was my mentor when she was undergraduate student, but now she is the graduate in the PhD course. And recently we submit the paper to the journal about the optical engineering for the MOOC system called Signal. And they are my peers when I was in France. And actually he was the boss of my group. And his former boss was the Louis Nel I showed you in the previous slides. And he is my advisor when I was a PhD student. And he is the theorist we have established the micromagnetic model together. Okay, this is the end of my presentation. Thank you for your attention. And I really hope you enjoy this time. And I hope this talk helps your future research and study. Okay, thank you so much.
Yeah, thank you. That was a nice presentation and good overview. We have time for questions. Any? Olive.
I'm wondering, say if there's any like downside necessarily, like they're used obviously about all the heat then, but is there like a downside that they're
So what is the definition of downsizing?
a bad part of it?
Ah. So the bad part of the spintronics you meant. Yes, actually there is. It is also very challenging to use spintronics for actual information devices. So if we want to use the spin waves for information transport, actually the signal is not very clear. Signal to noise ratio is not very high than conventional charge-based electronics, actually. And also, it is magnetic. So sometimes it is very, the magnetic field, external magnetic field can be, can destroy the information stored in this kind of materials. And also, yeah, I didn't talk that kind of things in these things. We also need the electric current to excite and control, detect the information. And the last one is we use magnetic materials. So generally, the resistance is much higher than, I mean, somewhat higher than gold and aluminum kind of things. So power, the energy consumption could be some problem.
All right, Tom?
It's related, but you said the soliton-like structures can require a mass.
Yes.
Does that mean they can generate heat like moving electrons?
The mass?
Well, if you're moving a mass, can you generate heat like moving electrons?
Yes, it can generate, yeah.
Is it much less than electric current maybe or something?
Maybe the spin waves. Yeah, in the case of spintronics, for example, spin waves, we don't need to move electrons. So just we need to change the spin orientation. Then this information, the excitation can propagate due to the exchange coupling between the spins. So ideally, there is no heat dissipation. But in real case, I already told that. To excite this kind of excitation, we need to apply some current, some electronic charge techniques. It can make some heat dissipation or energy consumption kind of problem. Yes.
All right, Jim.
Yes.
So, also the first part, having
Yeah. Second part. Yes. Oh. Yes. And the first question, the question is why I choose manganese 13, and the second question is what kind of chiral materials I can use for this work, right? Yeah, the first question, yeah, I choose manganese 13. There was a very practical thing, but there could be a lot of candidates. So actually, this is the field of automagnets that is a very active research field in spintronics at this moment. So there are a lot of automagnets candidates, materials. There are a lot of materials at this moment. So, but I choose this one because it clearly has spin-dependent band structure. And unlike conventional automagnets, it also have the bands also respond to different response for up state and down multiple state. In the case of general automagnet case, they have the same response, but they have different response this state and that state. So it looks more like the ferromagnets. I choose this one. It is more straightforward, and more practical reason is we have the materials in our chamber system. The second question, what kind of chiral materials can I use? Currently, I'm studying the conjugate, pi conjugate polymers. I don't remember the exact name of the polymers, but basically there's a chiral-induced spin selectivity effect. It's in many chiral materials in organic and inorganic systems. Actually, it first observed in DNA, and next it observed in the peptide, and also observed in the crystal, the tellurium, manganese tellurium kind of things. It has chiral atomic structures. So basically, I'm interested in all the organic, both organic and inorganic materials, which can have different symmetry breaking structures, left-handed and right-handed structures. I want to measure the spin property for any conductive materials that has interesting atomic or molecular structures. That's okay. Thank you. Multiple systems. Oh, yes, yes. No, no, it does not have a lifetime. Means that the spin structure, the lifetime of the spin structure. In this case, I don't have any clear picture about the lifetime. Actually, this is the kind of classical physics. We can explain it using classical physics. So we don't say about the lifetime about this structure. So it can last very long time. So very long time is year or tens of years. So without any external perturbations, thermal perturbations, or magnetic perturbations, ideally it can last very long time. Yeah. And also it, as I said, it forms by many spins. So it is not very affected, influenced by probability and quantum mechanical things at this point. Up here? Yeah.
What kind of experimental planet can do to detect different segments?
Yes, it is a good question.
I stopped sharing so people can see.
Yeah. Basically, I'm thinking about the conventional and the electrical measurement and optical measurement techniques. The optical measurement techniques is for the spin wave-like behavior, like a time-resolved Moog system. It can measure about terahertz order dynamics in this case. But I'm more interested in the current electrical measurement techniques. So yes, currently I'm interested in the anomalous Hall effect measurement. So I apply the electric current through the magnetic routine. And actually the whole signal is dependent on the order of the magnetic octopole orientation. So if it shows any dynamics of the octopole shows any dynamics, the whole signal changes in time. So my first goal is measure the whole signal using spectrum analyzer by exciting the dynamic mode under the excitations. But of course, I can try some very conventional FM ferromagnetic resonance techniques, because anyway, it generates magnetic field. So I'm not sure how, ideally it can be detected by conventional ferromagnetic techniques, but of course the signal is very small. So yeah, it is not very positive, I think. Thank you.
Right.
Oh, yes, sorry. Yeah.
Is there anything that say happens, especially on the boundaries that might, say result in instabilities or, ability to amplify or signal outside devices that will work?
So for the electrical measurements?
Yeah.
Okay, yeah, yes, thank you so much. Well, but yeah. So it's a question. Oh. Oh.
But then propagating the spin the material, but what happens if when you get to them?
Sorry, what is the meaning of the boundary? This.
Like the edge of the material.
So
You-
you have a sample of material.
Yes.
in the laboratory.
Yes.
Somewhere there's a boundary to it.
Yes, sample boundary.
Right. What happens there?
Okay. So yes, it's a good question. I haven't think about it. Actually, this is bulk material, so I didn't think about the boundary or edge effect on this kind of materials. Yes, some samples can show topological insulator kind of things at the boundary or edge, but I haven't seen any report about the boundary, the special effect at the boundary for these materials. But yes, I think it is good idea looking the other this kind of material.
It looks like it hasn't been really that relevant, but dynamics are working there. Just
Okay, thank you so much. It is very good idea, I think. Yeah, interesting. I haven't think about that.
Well, to follow up maybe a little bit on Kapil's question and maybe Nate's also, can you say more about experimental techniques? How large a sample of material do you need for some of these fairly novel materials? How large a sample can you even manufacture? What temperatures do you need? Do you have pictures of your lab? You showed us very nice animations, but how does this actually work?
Yeah, for these materials, yes, I have experience. Generally, I grow up the magnetite, the complicated magnets using sputtering deposition techniques. The temperature goes up to, 400 degrees Celsius, 500 degrees Celsius for the annealing. And the size is, of course, depends on the substrate, of course, this deposition technique. But the thickness is generally for this kind of experiment, about tens of nanometers. It's very thin, it's thin film. So in this kind of such as the quantum magnetic material research, I won't fabricate the samples at this university. I will request my colleagues for these samples from outside and make a patterning and use this for the, I will more focus on the characterization, the spin transport characterization, and if it is possible, the optical characterization for this kind of materials. So, yes, I will investigate more focus on their dynamics, not the fabrication.
All right. As for optical methods, do you see those more as a tool to study the fundamental physics, or do you envision in eventual applications in spintronics, optical methods can play a role there?
Ideally, yes, it is a good question. And my current plan is observation of the magnetic state in the non-Coriolis antiferromagnet using optical techniques. But by collaboration with my current research group, we can study about the terahertz signal excitation using this material because it has the potential to generate up to tens of gigahertz, even more than terahertz signals. That is very interesting research topic in this, the microwave, not microwave, but terahertz excitation field. Yeah, so in that case, we need to use the optical techniques because it is impossible to measure terahertz dynamics using electrical techniques. Yes.
Okay. All right. Any other questions in the room? All right. Then let's thank you again. And
Thank you.
yeah, thanks for the presentation.